For the remaining maybe 45 to 50 minutes, I'm going to cover the remaining topics on detached shock wave in front of a blunt body. Okay, so I believe Dr. Hugh have already provided the link to the slides, so you can download it, and you may want to enlarge it so that you can zoom in into particular section, right? Because if you are just looking at the PowerPoint slideshow, probably you miss a little bit in terms of the details. So in terms of the detached shock wave in front of a blunt body, so this is a sketch of a flow over a supersonic blunt body. So this is a supersonic blunt body. So we have a flow at Mach number more than 1. So you have a development of the shock wave, normally a bow shock, right? So this particular figure show curved bow shock which stands in front of a blunt body in a supersonic flow. Over here, the shock wave stands a distant delta. So this is the distant delta that we are talking about, which is defined as the shock detachment distance, right? So this is actually very close to the nose of the blunt body. Okay? At the point A, so basically this is the point A, the shock wave is normal to the upstream flow, hence point A corresponds to the normal shock wave. So what happened immediately right in front of the detachment distance, we can, that particular position is correspond to a normal shock wave. So a curved bow shock wave is one of the instances in nature when you can observe all possible oblique shock solutions at once for a given free stream Mach number M1. To see this more clearly, consider the previous theta beta Mach number figure as shown here, right? So where we have a determination of strong shock and a weak shock over here, right? So, and at various position A, B, C, C prime, D, and E. Yeah? So A basically at angle of 90 degree. Okay? So basically this is a normal shock, and then when we move upwards, B, C, C prime, where we have the sonic line over there, we have D, and at the edge of the bow shock, right, we have the value of E. So when we translate it into the theta beta Mach number lines, so it is actually represented by this particular curve. All right. So point A, which correspond to the normal shock, just in front of the, let me just put it on a laser pointer, right? Just in front of the sonic distance, okay? And point E correspond to the Mach wave. Point E at the edge of the Mach wave, and slightly above the center line at a point, the shock is oblique but pertains to the strong shock wave solution as in theta beta Mach number figure. And the flow is deflected slightly upward behind the shock at point B. So basically it is being deflected upward, all right, behind the point B. So this is point B. And as we move further along the shock, if we move further up, right, the wave angle becomes more oblique, and the flow deflection increases until we encounter point C. So when the angle become increases when we approach point C, okay. Point C on the bow shock correspond to the maximum deflection angle. So this is only one deflection, maximum deflection angle. So this is the point of theta is maximum deflection angle, right? What happened is that above point C, from C to E, all points on the shock correspond to the weak solution. So from C to E is basically pointing up to the weak solution, weak shock solution. Slightly above C and at C prime, the flow behind the shock becomes sonic. So basically, this is the sonic line where we put it as a value of less than Mach number 1, right? Above that, it is more than 1 when it is being deflected, right? So from A to C prime, the flow is subsonic. Behind the bow shock, from C prime to E, it is supersonic. So this is the region where Mach number less than 1, which is a sonic flow, and outside this region, where from C prime to E, we consider it as the supersonic regime. So because the velocity, sorry, the Mach number is greater than 1 at this particular region compared at this inner region within the delta, right? As a summary, the flow field between the curved bow shock and the blunt body is a mixed region of both supersonic and subsonic and supersonic flow. So this dividing line between the subsonic and supersonic region is called the sonic line, as shown in the figure that we have looked just now. And the shape of the detached shock wave, its this detachment distance delta, okay, detachment distance delta, and the complete flow field between the shock and body depend on Mach number at region 1 and the size and shape of the body as well, right? So the solution of this flow field is not trivial, or in other words, it is not significant. Let us look into example 3.7. So I put it as large as possible so that we can really utilize the area over here. Two streamlines crossing a detached bow shock in front of a blunt body at Mach 8. So this is not the blunt body. This is a streamline A. This is a streamline B, basically. So the blunt body is basically somewhere there, right? Consider the detached curved bow shock wave in front of the two-dimensional parabolic blunt body, which is drawn in this particular figure. Right? The free stream is at Mach 8. Mach number M1 equal to 8. Consider the two streamline passing through the shock at points A and B, as shown over here. Right? So the wave angle at point A is 90 degree, which is a normal shock wave. And at point B is 60 degree. So given the wave angle at point B is 60 degree, you have to calculate and compare the value of entropy, value of S, relative to the free stream for streamlines A and B in the flow behind the shock. All right? So let us try to resolve the issue. So the oblique shock properties studied in this chapter are derived based on a straight oblique shock wave with a uniform flow field behind the shock wave, as sketched in figure A, the concave corner, right? So we have the theta over there, right? We have the oblique shock. So this solution do not apply to the non-uniform flow behind a curved shock wave as shown in the current situation, right? So the straight oblique shock solution treated, however, give the shock wave properties at any local point immediately behind the curved shock wave if we know the local wave angle at the point. So therefore, immediately behind the shock at point A, because the shock is a normal shock, at that point we have Mn1 equal to 8, right? So reading from appendix B, for Mn1 equal to 8, we have the pressure ratio P2 over P1 74.5, and temperature ratio T2 over T1 is 13.39. So from our earlier equation, the entropy, we want to find the entropy, right? Entropy increase across the shock is given as this expression, right? So since we know that Cp equal to gamma R over gamma minus 1, putting down the numbers, you will get Cp to become 1004.5 joule per kilogram Kelvin. Then you can then use this, put Cp value inside the expression, you will get S2 over minus S1 equal to 1370 joule per kilogram Kelvin. So downstream of the shock wave, the flow along any given streamline is both adiabatic, means that it's no heat transfer, and reversible, means that no friction. Hence, the flow along a given streamline behind the shock wave is isentropic. Therefore, along the streamline A, the entropy is constant and equal to its value at point A just behind the shock wave. Thus, S2 minus S1 along streamline A equal to 1370. So basically, after behind the shock wave, normal shock, and in front, this is the value, all right, at streamline A. Immediately behind the curved bow shock at point B. Now we look at point B. We are given beta to be 60 degree. So we have Mn1, M1 is 8, sine beta, sine 60 degree is 0.866. You will then get Mn1 to become 6.928. From appendix B, using the nearest entry, Mn1 will become 6.9. So we have the pressure ratio 55.38 and the temperature ratio of 10.2. Thus, at point B, okay, so you put inside the temperature ratio and pressure ratio values, you will then get the S2 minus S1 at point along streamline B is equal to 1180 joule per kilogram Kelvin. So the entropy along streamline B is smaller than the entropy along streamline A, because streamline B passes through a weaker part of the bow shock wave. All right. Now, let us go into the last part of the oblique shock and expansion wave topic, which is called the Prandtl Meyer expansion waves. All right. So as we have already gone through earlier, in our previous lecture, we discussed on oblique shock wave that is occur when a supersonic flow is turned into itself, meaning that it is a concave corner. What happened? In contrast, when a supersonic flow is turned away from itself, where we have an expansion wave. So instead of a concave corner, we have a convex corner. So we have the theta down here instead of theta up here, right? As sketched here. So if it is like this, it is called a concave corner. You have an oblique shock. But if it is like this, the theta is down here, it is an expansion fan. All right. Where look carefully over here, the Mach number at region 2 increases. So the Mach number value increases compared to the Mach number at region 1, right? However, the density will decrease, the pressure will decrease, as well as the temperature will also decreases compared to the concave corner at oblique shock, which is the other way around. Now, let us consider an expansion wave case as figure below. So we have this center of expansion wave. So the theta is downwards. So we have properties like this. The expansion fan is bounded upstream by a Mach wave, which is the angle, which makes the angle mu1. This is the angle mu1, right? With respect to the upstream flow, where mu1 equal to sine minus 1 over Mach number at region 1. Okay, so the expansion fan is bounded downstream by another Mach wave, which makes the angle mu2. So this is the forward Mach line, and this is the rearward Mach line, because it is an expansion fan. So you have mu1 and mu2 over there, right? So with respect to the downstream flow, where mu2 equal to sine to power minus 1 over Mach number at region 2. So this is region 1. So this is region number 2, right? So we know that from our previous oblique shock lesson, right? So we can also write the sine mu equal to 1 over Mach number, where mu equal to the sine of minus 1 power minus 1 over times 1 over the Mach number. So assume the expansion through the wave takes place across a continuous succession of Mach wave. And since the entropy no change between the region where ds equal to 0 for each Mach wave, then the expansion is considered isentropic. And this is in direct contrast to the flow across oblique shock, which always experiences an entropy increase, right? So in our case now, the no change of entropy, ds, the change in entropy equal to 0, right? So the fact that the flow through an expansion wave is isentropic is a greatly simplifying aspect. An expansion wave emanating from sharp convex corner, as sketched in the previous figure and called as centered expansion wave. And Ludwig Prandtl and his student named Theodor Meyer first worked out a theory for centered expansion wave way back in 1907 and 1908, more than 100 years ago, 120 years ago, and hence such waves are commonly denoted as Prandtl Meyer expansion. So from the supervisor, the professor Ludwig Prandtl and his student Theodor Meyer. So they have this expression of Prandtl Meyer expansion wave. So from the previous figure, let us consider a very weak wave produced by infinitesimally small flow deflection of d theta and delta theta, as sketched in this particular figure. So this is the delta theta, a small change in the wave angle, right? So we consider the limit of this picture as delta theta because this is very small, so it is near to 0. Hence the wave is essentially a Mach wave at the angle of mu, right? Because it is nearly 0, we want to consider a very small change. So we just consider Mach wave at the angle of mu to the upstream flow, and the velocity ahead of the wave is given as v over there. So as the flow is deflected downward through the angle d theta, and the velocity is increased by the infinitesimal amount dv, right? And hence the flow velocity behind the wave is v plus dv inclined at the angle d theta. And recall from our previous derivation of the oblique shock wave using the momentum equation that any change in velocity across waves take place normal to the wave, and the tangential component is unchanged across the wave, which is equal to W1 equal to W2. W2. As in this particular figure, the horizontal line segment AB, so we have AB over there, with length V is drawn behind the wave. And also the line segment AC, A to the point down here, is drawn to represent the new velocity V plus dV. So basically, this is the velocity, and V plus change in velocity is A to C. All right. Examining the geometry in this figure, from the law of sine, right? The revision of sine rule is given down here. You may want to look back in terms of the sine rule, right? Where it applied to the triangle A, B, and C, right? We see that this expression can be written, and knowing from the trigonometry identities, right? So you can then rewrite the expression as this. Okay? And substituting both trigonometry identities equation into the sine rule geometry equation, we have 1 plus dv over v, which equal to the corresponding value for mu, right? And then for small change of theta, we can make the small angle assumptions where sine d theta is equal or near to the d theta itself, and cos d theta equal to 1. And then the above equations becomes this expression, which we can rewrite 1 over 1 minus d theta tangent mu equal to 1 over 1 minus x. And note that the function 1 over 1 minus x can be expanded in a power series for x less than 1. So you can have in terms of power series over there, by ignoring terms of second order and higher, so the equation can be written as this expression only. All right, rearrange that and rearrange this expression. We have d theta equal to dv over v over tangent mu, right? So knowing the trigonometry rules, so you get that from the triangle. We have tangent for mu, right? Tangent for mu is which is 1 over the square root of m squared minus 1, right? Tangent is this over this, and thus d theta equation can be written as this expression. So let us integrate the equation from region 1. From region 1, from over here, right, where the deflection angle is 0 and the Mach number is m1, to region 2, which is down here, where the deflection angle is theta, and deflection angle is theta, and the Mach number is m2. So you can use this expression d theta. We have, when you do integration, right, limitation is m1 to m2 to carry out the integral on the right hand side of the above equation, and where dv over v must be obtained in terms of the Mach number as follows. So we know that v equal to ma. So solving the expression, okay, from here, you can also have that dv over v of dm over m plus dA over A, knowing this speed of sound value, square root of gamma RT, right? Rearranging everything, and from the earlier expression in chapter 2, rearrange the equation, we have this expression, right? So differentiating equation above, we obtain this equation, and knowing dv equal to dm over m plus dA over A, so we equate back dA over A into the equation, then we have this expression. So you put this into here, you resolve it, put dv over v into equation and integrate it, then we have theta value, right? So look into the equation of theta, right? So we can note that the Prandtl Meyer function, v function of Mach number, which can be expressed as this, and solve the integration above, we will then get this expression, right? Also, we can write theta value in terms of the Prandtl Meyer expression V times the Mach number at region 2 minus Prandtl Meyer function V times Mach number at region 1. Okay, so that's where we get this Prandtl Meyer expansion with equation, right? Which is for a calorically perfect gas. And the Prandtl Meyer function is very important. It is the key to the calculation of changes across an expansion wave. Because of its importance, the value is tabulated as a function of Mach number in Appendix C. So you can then refer to Appendix C in your textbook, Anderson textbook. Okay? So the values of mu also being tabulated. How? And then the question raised is that how do the above resolve and solve the problem stated? That is, how can we obtain the properties in region 2 and from the known properties in region 1 and the known deflection of angle theta, right? So let us look into the steps proposed over here, where for the given value of Mach number at region 1, we then obtain the Prandtl Meyer expansion value, okay, times the Mach number, right, at region 1 from Appendix C, right, and calculate VM2 from the equation. So we want to know what is VM2 using the known theta of the value of obtained in step number 1, right? So step number 1, use the value in Appendix C and then calculate it from the equation down here, obtain M2 from Appendix C, corresponding to the value of VM2 from step 2, and then step number 4, the expansion wave is isentropic, hence P0 and T0 are constant through the wave, and that is T02 equal to T01 and P02 equal to P01. And from the earlier equation that we have already looked at, we can then have the temperature ratio value T2 over T1, right? So similarly, from equation of P0 over P, we can then get the value of pressure ratio P2 over P1. So since we know both M1 and M2 as well as T1 and P1, so these two equations, so this equation, the pressure ratio equation, as well as the temperature ratio equation, right, allows us to calculate T2 and P2 downstream of the expansion waves. So this is the Appendix C. If you look at Appendix C, the Prandtl Meyer function and Mach angle, so you have the value of Mach number, okay, the value of the Prandtl Meyer expansion parameters, the V, as well as the mu values, right? So this is the another example, right, where example 3.9 with respect to Prandtl Meyer expansion waves. Okay, a supersonic flow given at Mach number 1.5, so it is more than 1, and P1 given to be 1 atm and temperature is 288 Kelvin. So it's expanded through a sharp corner, right, through a deflection angle of 15 degrees. So the theta is given as 15 degrees. So you have to calculate M2, P2, T2, P02, and T02, and the angles that the forward and rearward Mach lines make with respect to the upstream flow direction. So they want to know what is the value of mu1 and what is the value of mu2, right? So the first step, from Appendix C, go to Appendix C, look at M1 equal to 1.5, V1 equal to 11.91. So you can go to Mach 1.5. So it is not here. I'm very sorry. So you have to go through the full page in in the appendix C, right? So you can then get the value of V1 for Prandtl Meyer expansion expression, right? So then you, from the equation that we have already looked at earlier, we then know that V2 equal to V1 plus theta, right? So 11.91 from the table, appendix C, plus the theta value given, which is 15, then you get V2 to become 26.91, right? So thus, from the nearest entry in the table, we get the value of M2, which is Mach number at region 2 equal to 2.0. So from appendix A, for M1 equal to 1.5, you then straight away read P01 over P1 and T01 over T1. And for M2 equal to 2, you can then read P02 over P2 and T02 over T1. Fairly straightforward over there. So since the flow is isentropic, right? So T01, T02 equal to T01 and P02 equal to P01. So from the expression, you will get P2 equal to 0.469 ATM and T2 equal to 232 Kelvin. All right. So from there, you can then immediately get the value of P02, which is equal to P01, and which is the value is 3.671 ATM. At the same time, the T02 equal to T01, you get the value of T02 equal to 417.6 Kelvin. Looking at the figure that being given earlier, the angle of Mach line mu1 is then obtained to become 41.81 degrees, and you read the corresponding mu2 minus theta, which is 30 minus 15, you get the value of 15 degrees. All right. So with that, let me just summarize the topic of oblique shock and expansion waves. So we have already gone through from the overview, oblique shock relation, supersonic flow over wedge and cone, shock interaction and reflection, detached shock wave in front of a blunt body, and finally Prandtl Meyer expansion waves, right? So what we can summarize from this particular topic or chapter 3, and some of the more important results are summarized as follows. And the first one is that an infinitesimal disturbance in a multidimensional supersonic flow creates a Mach wave, and that makes an angle mu with respect to the upstream velocity. And this angle is defined as the Mach angle, right? So it's being expressed as follows, right? Number 2 is that changes across an oblique shock wave are determined by the normal component of the velocity ahead of the wave. For a calorically perfect gas, the normal component of the upstream Mach number is the determining factor, right? So changes across an oblique shock can be determined from the normal shock relations derived earlier in chapter 2, which is the normal shock chapter. And by using Mn1 in this relation, we've been using this expression from time to time, where changes across an oblique shock depend on two parameters, right? So you can use the value of Mach number at region 1 and beta, or Mach number at region 1 and theta, right? So the relationship between Mach number at region 1, the beta and theta is given in the chart of theta beta Mach number, and which should be studied closely because you need two of any of these values to use the chart properly. And number 3 is that, as a summary, the oblique shock wave incident on the solid surface reflect from that surface in such fashion to maintain flow tangency on the surface. Oblique shock also intersect each other. We have already seen just earlier before the break, okay, the type of flow that intersect on each other depending on the situation of the complex geometry, and with the results of the intersection depending on the arrangement of the shocks. And finally, the governing factor in the analysis of a centered expansion wave in the Prandtl Meyer function, where we want to find V in term of the function of Mach number, the key equation which relates the downstream Mach number M at region 2, the upstream Mach number M at region 1, and the deflection angle theta is given as follows, right? So, which leads us to the usage of the table in appendix C, Prandtl Meyer expansion wave table. So with that, thank you very much.